Just as a reminder, what we were doing last time is we were uh, imagining that there was just a rod of some length L and of some mass M. And we assumed that the mass was evenly distributed throughout the rod. So one end wasn't heavier than the other end, it was uniform. And we computed that the center of mass, using this integral that we developed, that the center of mass is located in the middle of the rod, which is not surprising. That's where it should be. That's where your intuition would say. So now we're going to make things a little bit harder. What if the rod isn't uniform? You could imagine, having a rod which is steel on one end, and maybe it's a steel aluminum alloy. I don't think those exist, but imagine that it was. So it's really heavy on one end, and then it gradually becomes more and more aluminum, so it's really light on the other end. You could imagine that such a thing might exist, and you might be interested where the center of mass of that object is. So just as an example, I don't know why that's not in the middle. Let's work out just some particular non-uniform rod. A baseball, yeah, sure, that would work. A baseball bat thicker on one end, so it's heavier on one end. There you go. So the example that we're going to consider is the following. Suppose the rod, and by the way, the reason we're dealing with a rod is because it's effectively a one-dimensional object. We don't really have to worry about its size because it's cylindrically symmetrical. And the reason why we're doing that is because it's easier to handle these integrals as 1D integrals rather than double integrals or triple integrals. But in general, you could do this for any three-dimensional thing. So suppose the rod is twice as dense on one end, or twice as massive. It doesn't have to be dense. Twice as dense on one end as the other, and also that the density changes linearly. So the example here is you have a smooth gradient of between not dense on one side and very dense on the other side, and it just smoothly transitions in a linear manner. So we just need to start writing things down that we know. So first, let's just give the density at the light end a name. So we call the density, and remember, this is a linear mass density, so it's kilograms per unit length. It's mass per unit length. So 1 millimeter on the light end, you would multiply your unit or your linear mass density by 1/1000, and that would give a mass in kilograms. So we're going to call the density at the lighter end. We're just going to give it a name just as a placeholder. We're going to give the name lambda naught. And that would imply that the density at the heavier end it would just be 2 lambda naught. It's twice as dense on the other end. And we're not quite done because we'd like to know how the density changes with position, but we know that the density changes linearly. So we need a linear function. Call it lambda of x, such that, and let me draw a picture here. So this is the heavy end. This is the light end. Let's put x equals 0 here, x equals L here. It's going to have the same mass and the same length. I don't know why I drew the lighter end thicker, but I just tried to draw it accurate. We need a linear function that tells us the linear mass density, lambda, at different positions along x. And we need that function to satisfy the following equations. We need it to be that lambda of 0, because that's the light end, that should be equal to lambda naught. And lambda of L, that's the heavy end, should be equal to 2 lambda naught. Now, fortunately, any linear function is precisely determined by 2 points, and we have 2 points here. So we could just figure out what that linear function is. So what we would find, there's 2 equations, 2 variables. What we would find is that lambda of x, you could go and solve. Lambda of x is, say, mx plus b. We would find, after doing this solving, and then you could factorize, is equal to x divided by L plus 1 times lambda naught. And hopefully you can check in your head. If x equals 0, you get lambda naught. If x equals L, you get 2 lambda naught. And this is a linear function because it only has 1 power of x, so this fits the bill. It just, the only reason I wrote it in this format is because it's easier to check off the top of your head that it works. Okay, so now that we know what lambda of x is, we can actually go and we can compute where the center of mass is. So we know that it's not going to be in the center, right? It shouldn't be. So I'll leave that up to you, but it's two equations, you have two equations, you have two variables, and so you can solve for those two variables, m and b, and then you can just factor and rearrange. We know the center of mass is not in the center of the rod, right? If it was in the center, that would mean that there's the same amount of mass on the bottom half as there is on the top, but the bottom half has less dense material, so there would be less mass in the bottom half than in the top half. So we know that the center of mass should be somewhere closer to the top. We just need to figure out how or where it is. So we can do that just by using the integral that we developed last time. So the x coordinate of the center of mass, please scroll. Remember, it's given by 1 divided by m. It's the weighted average of positions where it's weighted by its mass, times the integral of x dm, where this integral is over the whole rod. Just as a refresher, xcm would be something like m1 x1 plus m2 x2 plus ... divided by m1 plus m2 plus ... And all we're doing is we're generalizing it where these chunks of mass are very, very small, and that sum becomes an integral. Right, okay, but what is dm? Well, remember last time, we want to know what dm is in terms of dx, because we want to do an integral, like we want to do a spatial integral. We want to add up the chunks as we go higher up in x. We don't want to add up the chunks as we go higher in m. That's not a very sensible thing to do. But remember from last time, it's always the case that dm is equal to lambda dx. Now this is only for one-dimensional problems. If you have two-dimensional problems, then it would be a 2D variable, or a 2D measure. It would be like dx dy or something like that. But in one dimensions, like like a rod, this is exactly what it is. And so this lambda here, unlike last time, this lambda is just a function. It's not a number. So, and we know what that function is now. It's lambda of x. So we can compute then. X is supposed to be center of mass, right? No. This is the center of mass. This is just the variable x. So the center of mass is 1 divided by m times 0, the integral from 0 to L, of x times lambda of x dx. Right? I just substituted in what dm is. And I put lambda of x because lambda of x is a function in this case. So we can do this integral. Simplifying, we get lambda naught over m times the integral from 0 to L of the integral x over L plus 1 times x dx. And so now we can just work out this integral. And it's not particularly hard. You get lambda naught over m. This is the first term is quadratic, the second term is linear. So you get x cubed divided by 3L plus x squared over 2, evaluated from 0 to L, which is lambda naught over m times L cubed divided by 3L plus L squared over 2, which is just equal to 5/6 lambda naught L squared over m. All right, so far, this isn't quite a useful answer because we still don't know what lambda naught is. So how do we get rid of that? Because this should be a position. It should be like some number times L. In the past, for the uniform rod, it was L over 2. We need to figure out what L naught is. Sorry, what lambda naught is. We just kind of gave the density at the bottom a name, but now we actually need to go and figure out what that density is. But we have one more trick up our sleeves. The total mass, m, is given by an integral just as well. It's an integral over the rod of just dm. You just add up all of the chunks and you get the total mass. And so we can rewrite this in terms of an integral from 0 to L of lambda of x dx. And then we can simplify this and do the integral, 0 to L, x over L plus 1 dx, which is just lambda naught times x squared over 2L plus x evaluated from 0 to L, which after doing some algebra and substituting in L, you get 3/2 lambda naught L. And so what we can do, this is all equal to m, so we can solve for lambda naught in terms of m and L, which is what we wanted to do. And that results in the following statement that lambda naught is 2/3 m over L. So the fact that the total mass is given in terms of this linear mass density is useful. It lets us figure out one of the parameters in our linear mass density function. All right, so then let's take that, plug it in here. And what we find is that the center of mass position, the x position of the center of mass, is 5/6 lambda naught L over m. I'm missing a squared, which is equal to 5/6, well, lambda naught is 2m over 3L times L squared over m. And so we can simplify and we get 59. You get 10 up top, 18 down below, you get 5L over 9. And so this is the position of the center of mass. It is 5L over 9 units above the bottom. And so, that would be like 60 or just about 56% up. So this would be the center of mass. And the point is that it's not at the center. It's slightly closer to the heavier end. And that's exactly what we expect. We expect it to be closer to the heavier end because there's more mass on the heavier end. And the center of mass is supposed to be the place where there's the same amount of mass on one side as there is on the other side. That's what your intuition should be for the center of mass. All right. So now if I just gave you some linear mass density function, lambda of x, or if I gave you a whole bunch of points, said the density function at x equals 0 is lambda naught, the density function at x equals a quarter is 2 lambda naught, at a half is 4 lambda naught. And so if I just gave you something, you could figure out what the linear mass density is as a function of position. You could figure out what that one variable is that fixes the linear mass density by solving for the total mass in terms of lambda. And then you could just find the center of mass for some arbitrarily given lambda of x by doing an integral. So you guys have the tools now. Now it's just a matter of how good you are at doing integrals. And typically these integrals will be polynomial in nature, which aren't hard. But the point is the trick is, there is no trick here. You just do an integral of 1 over m, or the center of mass is just this thing. That just is the x position of the center of mass. And then you just do an integral. Now, just as a key point, notice that I chose the coordinates x equals 0 and x equals L. That's what made the bounds 0 to L. But if I had put x equals 0 in the middle and had either side be x equals plus or minus L over 2, that would have changed what the bounds look like, and it would have changed the integral. And it would have changed what lambda of x is, because I would have had lambda of negative x over 2. Sorry, negative L over 2 is lambda naught, and lambda of positive L over 2 is 2 lambda naught. The point is you can choose whatever coordinate system you want. You just have to be consistent. All right, let's move on. So we know how to compute the center of mass. Now we started this whole discussion talking about rotational inertia or moment of inertia. And so now we have the tools to do that. Now that we've gotten practice with center of mass, we can do the same thing with the rotational inertia. So let's start with a uniform rod. And we're going to do much the same. It's just the formula is different here. So a uniform rod. And we're going to put the pivot point, because remember, for the rotational inertia to compute this, you have to know about which point you're imagining this rotation occurs. So that's called putting the pivot point somewhere. And we're going to put the pivot point at the bottom of our rod. We're going to put it at x equals 0, which is the bottom of the rod. So just so then we're using the consistent coordinate system. So the picture is you have your rod, you have x equals 0 at the bottom, and our pivot is right there. So imagine that this is the moment of inertia that this object would have if it were swinging around that pivot point. Then we have x equals L up here. All right, so I mentioned this last time. The moment of inertia, I, is given as the sum, or as the integral, over the entire rod of r squared dm. Now here, this r squared has special meaning. This is the distance from the pivot. So in particular, this distance should always be positive. I mean, you're squaring it anyway, so it'll end up positive, but this distance is positive. Now we don't have to worry about like which point on the pivot on the pivotal axis you're worried about, because this is in 2 dimensions. So the pivot is just a point in that case. But if you were imagining like a real world thing where, say, this pen was the axis of rotation, that distance would actually represent, that distance would actually represent the distance from the point, or the closest distance from the pivot to the object. So the distance that I would compute, it's really hard to hold, the distance and to display. The distance would be from the tip of the pen to any point on the phone, rather than from the back of the pen to any point on the phone. It's the closest distance from the axis of rotation to the point we're interested in. But nonetheless, that doesn't matter a whole lot for one-dimensional or for 2D rotation, because the pivot axis is just a pivot point. All right, so we need to figure out a few things. We need to figure out, what does this integral mean? We need to figure out what's the coordinate expression for r squared, i.e. in terms of the coordinate x. And then what's dm in terms of x, in terms of dx. So first let's answer the question, how far is a chunk at position x? So imagine just like some chunk here at position x from the pivot. Well, that's a pretty easy question. It's just x units. So using this coordinate system, the distance is just the x coordinate. But again, if we had put x equals 0 in the middle, that would change the formula in terms of x, because the pivot would still be at the bottom. So that means in this case, r is equal to x, because r is the distance from the chunk of interest to the pivot point, and that distance is just given by that pivot point, or that chunk's coordinate position. We also know that dm is equal to lambda dx, like before. That's still true. Everything? Okay, I unfroze. So again, we want to integrate over the entire rod using the coordinate x. So that means we integrate from x equals 0 to x equals L. So let's do that. So that means that I is equal to an integral from 0 to L, x squared lambda dx. Now, before, when we were doing this uniform rod business, we figured out that for a uniform rod, lambda is just equal to m over L. It's just the total mass divided by the total length. So that's what we're going to substitute in. So what we get is, we get this, after doing this integral, we get lambda L cubed divided by 3, which is just ml times L cubed over 3, which is just ml squared over 3. And so this quantity here, this is ml squared over 3. This is the number that is the moment of inertia about one end of a uniform rod in here. I'm going to turn off my video for a minute, see if it makes it easier. Oh, it crashed. Cool. Oh, nope. Okay, I'm back. Excellent. All right, I'm going to turn off my video for a bit, see if that makes it any better. All right, so I'll just continue like this. Yeah, it does seem like this always happens on a Friday. Is it better? Can you guys hear me all right? Can you see me writing? Okay, so maybe we just stick with this for now. But you won't get to see my lovely face anymore, but it's the price we pay, right? It's the price we pay for science. Right, so this ml squared over 3, this is just a formula for computing the moment of inertia of a rod that has uniform mass density when the pivot point is about one end of the rod. Notice that this doesn't care at all about the coordinate expression that we used. It doesn't care that we chose to put the x equals 0 at the bottom. We would have gotten the same answer if we had chosen to put x equals 0 in the middle, for example, or x equals 0 anywhere else. We would have gotten the same thing, and this is just a this is a property of a uniform rod. If you put the pivot at the bottom, you get ml squared over 3 for its moment of inertia. Now, let's think about the units here. The units of moment of inertia, we saw that that's supposed to be equal to a distance squared times a mass, right? It was, when we were computing it for a discrete set of objects, it was the mass times the distance from the object squared. And this has those correct units. It's mass times L squared. And then there's just this factor of 3 that comes from the shape of the object. So the important point here is that the formula that you get for the moment of inertia, and there's a whole bunch of these, like you can think of what's the moment of inertia of a rod about its center, or what's the moment of inertia of a disk, and all of those things. The formula that comes out always has the same units. It's always mass times distance squared. But the rest of the formula, in this case, it's the 1 over 3 part. All of that comes from the shape of the object and where you're pivoting about. So it's not quite as easy to say that it's exactly equivalent to mass, because the formula that you get, that you would plug in, that would correspond to the mass of an object, depends on the shape and where it's pivoting. All right, so let's do the same thing for the non-uniform rod. So we're going to use the same rod that we had. So lambda of x is x over L plus 1 times lambda naught, where lambda naught is 2m over 3L. That's still true. That's just a property of the rod. So this would tell us that lambda of x is just 2m over 3L times x over L plus 1. And you can check the units, by the way. This has units of mass per kilogram, or mass per distance. All right, so we do the same thing that we just did. The moment of inertia, I, it's always equal to the integral over the whole object, in this case it's the rod, of r squared dm. And so in this case, just like assuming that we're using the same coordinate system, this r is x, this dm is lambda dx, this rod is an integral from 0 to L. And then we just do it. Integral from 0 to L, x squared, and then I need a 2/3, 2m over 3L, x over L plus 1, dx. And I'm not going to step you through the calculation. You guys all know how to do integrals. But the end result is you get 7/18 ml squared. Now, this is only for a uniform rod that is twice as, or for a rod whose density varies linearly and is twice as dense at one end as it is at the other. So this is probably not worth memorizing. This one is worth memorizing because it's super common. But this example that we just did, significantly less general and less useful. So it was just an example. But one thing to note is that the formula here is bigger. It's greater, has a larger moment of inertia than the ml squared over 3, right? 7/18 is bigger than 1/3. And so you might ask why that is the case. Well, if you think about it for a little bit, you might see that, well, the linear mass density rod, or the rod that has whose density varies linearly, that's going to have more mass further away from the bottom of the rod, right? It'll be heavier over here than it is over here. That's just because it's more dense on one end than the other. And we saw that the moment of inertia of a given object is both related to how much that object, or what the mass of that object is, but also how far away from the axis of rotation that mass is. And so in this case, as we'll see in general, the further away from the axis of rotation that the mass is, the larger the moment of inertia. So if you have a lot of mass far away from the axis of rotation, you'll have a larger moment of inertia. On the other hand, if you guys were super enterprising, you might go and you might find the moment of inertia about this non-uniform rod, but with the pivot point at x equals L and not at x equals 0. So you put the pivot point on the heavier part. And I would suspect that you would find that the moment of inertia is smaller because because a large percentage of the mass is concentrated near the pivot point, which reduces its impact on the moment of inertia. So I think you're going to do this in discussion where you have more practice calculating moments of inertia and center of masses. Also on the homework, there is more practice, in particular problem. I could have sworn problem 1. Yep. Problem 1 is a more complicated version of this. Instead of having the linear mass density vary linearly, it varies quadratically. And I give you instead 3 data points, and you can go and you basically perform this whole, you go through this whole process of finding the moment of inertia, finding the center of mass, finding, and all of that business. So you're going to get more practice, but it's not a conceptually challenging thing. It just involves thinking about the geometry of the problem. What's x equals to, what about a rod that isn't straight? That makes it become a two-dimensional, that requires that it become a two-dimensional integral, especially if you're at, let me leave it at that. Like, it's doable, but it requires a two-dimensional integral in most cases. But so you guys now have the tools, at least in principle, to find the moment of inertia of an object, or at least you know what a moment of inertia is. Now, I'm not going to show you how to calculate the moment of inertia of a disk. If you know how to do double integrals, then you could go look that up. It's not particularly challenging, but it does require some integral calculus you might not have. But what I can tell you is I can just tell you what the answer is. You can go Google most of these things. What's the moment of inertia of a disk? What's the moment of inertia of a cube? What's the moment of inertia? And like, there's a table on Wikipedia that has all of these things. They're well known. And so what we're going to proceed with is less about how to compute the moment of inertia and more what you can do with it once you know it. So we're going to talk about something else, or something that's slightly unrelated, which is this idea of principal axes, or principal axes, if you want to talk about heavy, sharp things. So real objects, like objects in the real world, phone, you can't see. Let me turn my video for a minute. Phone, pen, pocket knife. Real objects are three-dimensional, right? It seems like it's probably chilled out, so maybe I'll just leave the video on. They're three-dimensional, and so in a sense, you'd expect there to be 3 independent axes of rotation, right? For example, take the phone. It could rotate this way, it could rotate this way, or it could rotate this way, right? There are 3 perpendicular axes of rotation. Come on. Can you guys still see me? Well, I'll continue. Real objects have 3 independent axes of rotation. Actually, let me check the Discord, see if anybody's pinging me. Okay. Yes, real objects have 3 independent axes of rotation. Stop video. God, I don't know why it freaks out when I try to stop the video. Anyway, and each of those axes, because they're different axes and the mass is distributed differently, each axis has its own moment of inertia. And the reason for that is basically that if we look at the phone example again, oh, my video, God, this is so frustrating. Trying to get through material that I have to get through. Okay, good, you can't see me. All right, I'll keep the video off. I'll just draw a picture. So imagine we have like a phone, right? Or like a rectangle or something. So if we imagine an axis that passes through the middle, like this, most of the mass is close to that axis, right? And so it will have a small moment of inertia because the moment of inertia is related to both the mass of the object and how far away that mass is from the axis. And you know, that axis passes through the middle of most of the mass, so it's going to be relatively small. The moment of inertia will be small. Whereas if we instead had the object the same object but with a different axis, maybe the axis goes like this, passing through the middle like that, more of the mass is further away. And so this would have a larger moment of inertia. And so you could see that for any given object, it will have three, we call them principal axes, that each have their own moment of inertia. And it turns out the principal axes, or these axes, these very special axes that are perpendicular to each other. Oh, thank you. These axes are called the principal axes. And importantly, they all intersect at the center of mass. So one way to see this is like you'd find where the center of mass is, the point where the center of mass is, which might be, here for the same object. And then you'd put three axes through it. And those axes would be oriented in some way that they go with the three primary directions of the object. And that was in air quotes because you couldn't see it. Now, for more complicated objects, those axes might not be obvious to figure out what they are, but there is a method to doing it. But for simple objects like a cube or like a rectangle like this, or for a rod, it's more straightforward. You can kind of just guess what they are based off of the shape. But the bottom line is that you have three perpendicular axes, all of which pass through the center of mass, and they all have different moments of inertia. I mean, it's possible that some of them are the same, like imagine a sphere, for example. It will also have three principal axes, but because it's completely symmetric, all of the mass is the same distance from any axis that you choose that passes through the center of mass. So all three principal or the moments of inertia of all three principal axes would be the same. I think it's 2/5 ml or mr squared, but don't test me on that. Right, but the question is why do they center at the center of mass, or why do they intersect? Like this, the principal axes are calculational tools. They're not like, they don't exist in real life. They're there to make some of the calculations easier because it makes it for reasons that should become clear later. We didn't have to do that though. So the question is what makes it easy, or what makes putting principal axes there easier for us? Why is it better to put them there? And the answer boils down to the fact that if you have a body just like floating in space, any freely rotating body that doesn't have any, that's not like fixed to anything, like just imagine like a rock just floating in space, it might be rotating or something. It will be rotating about an axis that passes through its center of mass. That is always true. And so that's why we put the principal axes there. It's kind of like the least biased choice of where you could put the principal axes, because it's the one that doesn't require any external forces to get rotation. Now, as for how we know that's the case, that a freely rotating object would rotate about its center of mass, about an axis that passes through its center of mass, that's a homework problem. So I want you guys to think about that some more. What a hint though is that it might be useful for you to consider what would happen if the object rotated about a point that if the object rotated about an axis that didn't pass through the center of mass. What would that say about the location of the center of mass? And what would that say about whatever forces and so on that might be present? That's the hint I'll give you. Now, the principal axes are useful for the following reason. Or for the reason that will be coming shortly. So we need to talk about the additivity of rotational inertia and the parallel axis theorem. The parallel axis theorem. Theorem is such a Latin sounding word. So before I proceed with explaining what all of this means, let's just consider an example. So suppose we have two blocks, or suppose we have two bodies, I suppose. We have two bodies, both rotating about the same axis. So one way to think about this would be like, imagine hard to do this without you even being able to see me, but imagine that like you glued two rocks together, right? We can treat each of those as separate bodies just attached to each other, and then just rotate the whole thing about some axis. Then you could consider both rocks as rotating about that axis. They're both doing their own thing. They just happen to be doing it in sync. They're rotating about the same axis. So the question is how do we combine the moments of inertia of just one of the rocks with the moment of inertia of the other rock to get the moment of inertia of the whole system? Just writing down what I just wrote. What is I for the combined system? I being the moment of inertia. Well, it turns out, and you can hopefully kind of intuit or grok why this has to be the case, the moment of inertia for the system of those two bodies that are both rotating about the same axis, it's just the moment of inertia of one plus the moment of inertia of the other, which is to say that moment of inertia is additive. And that's just like mass. If you're curious, the reason for this is because the moment of inertia of the system, which would be this would be I cis equals r squared dm. We know that we can split integrals when you're integrating over something. So as long as you integrate over the whole whatever, it doesn't matter if you split it up. So you could write this as the moment of inertia of body 1, r squared dm, plus the moment of inertia of body 2. And the important part is that those r's refer to the distance from the same axis. And then this is just equal to I1 plus I2. That's all. It's just saying that you can split integrals, which we all know is true. All right, so the last useful tool is this business of the parallel axis theorem, which is where these principal axes really, really shine. So the parallel axis theorem is a powerful tool. Makes it really easy to compute moments of inertia of something complicated without, or just by knowing the moment of inertia about some other place. So the parallel axis theorem relates moment of inertia about an arbitrary axis to the moment of inertia about a parallel principal axis. So the principal axes, again, you can just choose them, and as long as all three of them are perpendicular to each other, you can just choose what direction they go in. You can choose one of them, and the other two have to be perpendicular to it and perpendicular to each other. So we just so what the parallel axis theorem says is, if you have some axis that you want to find the moment of inertia about that axis, just find the moment of inertia about the principal axis that points in the same direction, and then you can use that to find the moment of inertia about the arbitrary axis. So I'll write it out as an equation. So this what I'm about to write is the parallel axis theorem. So the moment of inertia about the arbitrary axis is equal to the moment of inertia of the parallel axis that runs through the center of mass. This is the principal axis. So I'm putting parallel CM. So, and I'll draw a picture. It'll be more clear. Plus the total mass of the object times the distance squared between the two axes. So let me draw a picture just to make this clearer. And I'm trying to replicate the picture that's in the notes, so bear with me. It's supposed to be like a stake or something. So let's say that the center of mass was here. So we know the principal axes pass through the center of mass. And let's say that we are interested in the moment of inertia about this axis. So this is our arbitrary axis that we want to find the moment of inertia about. Well, you would have to know something about like You'd have to know everything about this object. Whereas if you just knew the moment of inertia about the parallel axis that passes through the center of mass, this would be a principal axis because it passes through the center of mass. And you know this distance, d, it's like the distance between the two lines. If you know one of the moments of inertia, you can find the other. So let me work through an example. And m is the mass of the whole thing, by the way. So let's say that we want to know the uniform, we want I for a uniform rod rotating about the center of mass. So what we calculated earlier was we found the moment of inertia about one end, but this time we want the moment of inertia about the center of mass. We want the pivot point in the middle. We're going to assume that this has length L, like usual. So we know that the center of mass is in the middle. So we know what position that's at. That if this down here is x equals 0 and this is x equals L, center of mass is at x equals L over 2. We calculated that already. Also, we know that the moment of inertia about one of the ends is equal to ml squared over 3, right? It's symmetric, so it doesn't matter which end. So we can use the parallel axis theorem. Parallel axis theorem to find the moment of inertia about the center of mass, right? So let's do that. So the parallel axis theorem says the moment of inertia about some arbitrary axis is equal to the moment of inertia of a parallel axis that passes through the center of mass times the mass times the distance between them squared. So in this case, the parallel CM, this is ICM in this case. That's the axis that was passing through the center. This axis, well, we can choose that arbitrarily. So let's just choose this to be I end. So then this distance is the distance from the end to the middle. So then we can solve for ICM. So we would have I end equals ICM plus m L over 2 squared, because the distance from the end to the middle is L over 2. And so we can rearrange. The moment of inertia through or about the center of mass is ml squared. This is ml squared over 3, remember? It's ml squared over 3 minus ml squared over 4 from subtracting this over to the other side. And so we can simplify and we get that the moment of inertia about the center of mass is ml squared over 12. So this is, so just like how I said that the moment of inertia about one end of a uniform rod is ml squared over 3, this just is the moment of inertia of a uniform rod about its center. So you'll see this formula pop up a lot too, because it's a fairly common thing. Like, again, imagine just like spinning a baton. If you're holding it at the center, this is the moment of inertia that it would have about that axis. So hopefully you can see that the parallel axis theorem is powerful. It basically lets you compute the moment of inertia about any axis as long as you know the moment of inertia about some axis, which is super handy. By the way, just as an aside, this moment of inertia, it's smaller than the moment of inertia about the end. 1/12 is smaller than 1/3. And the reason for that, and it should kind of make sense, is that the moment of inertia cares, like I've said a million times, it cares about the mass, but also where that mass is. And the closer the mass is to the axis of rotation, the smaller the moment of inertia. And so the center of mass is kind of defined. It's more rigorous than this, but it's kind of defined as the place where all the mass is closest to. So of course the moment of inertia about the center of mass will be small, or smaller than the moment of inertia about any other place, because it is the one place in the object where the mass is closest. Everywhere else, there will be some mass that's closer, but most of the mass will be further away. And so in fact, you can see you're always adding a positive number to the moment of inertia through the center of mass. And so so the moment of inertia about any other axis will always be larger. So there is some sensible intuition there, I hope. All right, so we have about 5 minutes left. How many pages left of notes do I have? I have a lot, so we're gonna have to go over a lot. Oh, actually, I don't think that all of this is necessarily needed for Monday, but yeah, I'll just get started, and then we can continue next time. So we are now done with the 1.5 lecture long interlude on how to compute these things. Now we actually need to talk about why we care about moment of inertia and location of the center of mass and all that at all. Like I promised that this would be useful for physics. Let's actually do some physics now, because so far we've kind of just done math. All right, so let's talk about the dynamics of rolling objects. Of rolling objects. Right. So we already know that like if you have an object like on a merry-go-round or a Ferris wheel, merry-go-round, that there's a relationship between the rotational speed and the linear speed, like how much distance they're covering over time. And so we know that there is some relationship between rotational and linear motion. And that relationship, it becomes manifest in a particularly common phenomenon. Particularly common and so that phenomenon that I'm talking about is rolling without slipping. Without slipping. Underline that because it's kind of a technical term, or at least I will use it as one. And also this is known as perfect rolling. So let's talk about what rolling without slipping is. Well, first of all, just intuitively, it's kind of what it sounds like, right? Imagine like a tire rolling. It's not skidding on the ground, it's just rolling perfectly. Like there's no sliding between the bottom of the tire and the surface of the asphalt or whatever. So that would be an example of rolling without slipping. Anytime something rolls while it goes down a ramp without like skidding out at all, that would be rolling without slipping. So the question is why is this important? Yes, hydroplaning would be rolling with slipping. Yeah, exactly. Well, it turns out this is one of those few times in an intro physics class where a lot of the assumptions that we've made are just correct rather than approximately correct. So when two surfaces slip, think like a block sliding along the ground, the change in thermal energy of the system is not equal to 0. It typically increases. However, rolling without slipping ensures, at least from yeah, well, I'll clarify in a minute, ensures that the change in thermal energy is 0. And that's at least there is no kinetic friction. So what causes rolling without slipping is that the static friction between the two surfaces is large enough, but the round thing, the wheel, can rotate. And so the static friction prevents the two objects from moving relative to one another, but doesn't produce sliding. And the sliding is what causes the increase in thermal energy. As we've seen before, static friction can't do work. It just doesn't do work. Or rather, it doesn't. So static friction can do work, but what it doesn't do is it doesn't produce thermal energy because there's no rubbing going on. And so the implication here is that the mechanical energy is conserved when an object is rolling without slipping, which is super useful. It means that we can use our energy conservation equations no problem without having to worry about like energy loss. The other reason why it's important, and then I'll end today's lecture just after I draw a thing, is that the distance traveled is related to the total angle rotated, related to the total angle So what I mean by that is like if you have like the ground and then you have a wheel and then you have that wheel later on at a later point, if you track a particular position to a later position, like after it's rotated, the distance that it will have covered, x, is equal to r times the distance, the angle that it rotated through, which implies that the speed, like the translational speed that the object moves at, which is d dt, and this is the same, this goes back to the things that we talked about before, this is just r theta, which is just, d dt of r theta, which is just r omega. So the point is when an object rolls without slipping, the angular speed of the object is related to the speed at which the object rolls, and that's super useful. All right, so does the surface material change that? No, it doesn't. Unless they're slipping, rolling without slipping doesn't care about the surface material. All right, I'm going to stop recording.